frequency. I'm Vishu.
I'm Ava.
And I'm Hannah.
So what are stars? Stars are big, bright spheres of plasma, and they're usually composed of hydrogen and helium. There are approximately 200 to 400 billion stars in the Milky Way galaxy alone, which is a lot. And there are like 1,000. There are like 1,000 other galaxies, so there's like 7 sextillion stars in the whole universe. And larger stuff, the most common, like the star we're most familiar with is the sun because it's like the nearest to Earth, so we're able to observe it and learn more about it. And larger stars tend to live shorter because they use up more energy, but they do shine like more brighter.
So this graph we thought would be a good representation of the range of the luminosity of stars and even the size. So on one side of the spectrum you have brown dwarfs, which are about 1/10 the size of the sun, but on another side you have very high mass stars, which is a pretty self-explanatory title. They're like 20 times the size of the sun. And where supernovae come into this is that when a star dies, depending on its size, it meets different kinds of fates, basically. So high mass stars and very high mass stars end up becoming supernovae, and then high mass stars, that's not what happens. High mass stars end up becoming neutron stars, which are very, very densely packed stars. And a good image to illustrate this is imagine the mass of 50 million elephants inside a thimble. That's how densely packed high mass stars are. And very high mass stars end up becoming black holes.
Okay, so what we had to do when we first got our data set, which courtesy of Jillian, because she helped us find it, it showed us the spectral types of stars, but we didn't exactly know what those meant. So this is like an example of what each spectral type means for each type of star and the information that it gives just based on the spectral type, which is what we used for most of our graphs.
So these are some of our research questions, and as we explored our data, it's such a huge data set that we just kept coming up with them, and we thought, hey, why focus on one when you can have 3? So our first one was, what percentage of stars become supernovae? That was the one we started with. Second one was, what spectral type are the majority of stars? And our third one was, how can we use parallax to calculate distance in space? And Hannah will explain more about that. And overall, we just wanted to explore the characteristics of the majority of stars in our universe. Oh, okay, and just like a few quick words on our data set. It's the Hipparcos star catalog from a mission that went out in 1992, and it's a very high precision catalog, so lots of information about more than 118,000 stars, so we had a lot of data to work with.
So parallax is basically our view of an object based on where we're standing. So this image shows 2 people standing at opposite sides of a tree. And so the person on the left side will see that the tree is to the right of the moon, while the person on the right side of the tree sees that the tree is to the left side of the moon. So this is basically how it works in space when the Earth rotates around the sun, because it's constantly changing positions throughout the year. And so scientists use parallax to measure the distance of stars from the Earth. And so basically, when the Earth is at this position, it can only see the star from here, and when the Earth is here, it can only see it from there. And so we use the equation 1 divided by p divided by 1,000 to figure out the distance that goes directly. And so yeah, the parallax is usually bigger when the object is closer to you, and the parallax is smaller when it's farther away. So in this Python code, we first imported the data, and we used the function, like I said, 1 divided by parallax divided by 1,000 to kind of insert the parallax of each of the stars to figure out the distance. And so we iterated through the code in this line of code, and yeah, to add the data to the list, and it basically ran through it and calculated the distance using that equation, and as a result we decided to create a histogram. from the sun, and on the y-axis it shows the amount of stars, and on the x-axis it shows the distance in parsecs. And parsecs, 1 parsec usually means 3.26 light years. And so we found that the majority of the stars, approximately 90,000, is near the Earth, compared to like 500 parsecs. And the negative numbers are just errors because the stars were just so far off that we can't really figure out more about it. But scientists have like created a new satellite called Gaia that is like better at finding out the data and making it more accurate.
So another graph we made was the percentage of spectral types of each star. So basically what we did first was we have, as we did in the other code, the CSV file, we read through it. And these are just the different spectral types of stars. So we have A, B, F, G, K, L, M, O, and T. And we went through the CSV file and we found all of the stars that were of each type and added them to each list. And then we graphed it. It's not, okay. We graphed it based on the lists and we color code. This is just like to make the graph, and because it's percentage of a whole, it became a pie chart. And it ended up looking like this. And on the side, it's just the printed values of each type of star. So the A-type star, B-type star, like the number of each type. And the majority, or around, the majority of the stars are F, G, and K type stars, and all 3 of those are in the low mass category of stars. And then just because the top was cluttered, that's what it looks like when it's zoomed in. And when it says 0%, it's just because, for example, the L-type star only had 3 occurrences. And in a data set that large, it would equate to a very small percentage. And then this is a code first graph for the stars that will supernova, which was our original research question. And this basically does the same thing except for placing stars into 2 lists, supernova and stars that won't result in a supernova. And this is just the code for the graph. It ends up looking like this. So as you can see, a majority of stars won't supernova, and those are the number differences on the side. And then this graph was the code for the percentage of each massive star, and the masses is what determines whether or not it will go supernova in the first place. So again, it's just categorization between low mass stars, medium mass stars, high mass stars, and very high mass stars, and this is the code for the actual graph. And it ended up looking like this, and these were the numerical values. So the high mass stars and the very high mass stars are the stars that will actually turn into supernova, and compared to the other 2 categories, they're very small percentage. And that's just zoomed in so you can see better.
Okay, so what we ended up with were largely 2D representations of our data. So in our data visualization part of our course, we actually became familiar with the software that enabled us to represent our data except 3D. So I'll just load that and talk a little. So it's called PartofView, as you can see, and it's actually a software developed by people at the museum. And the really cool thing about this software is that it is very accessible. You could go home right now and download it onto your computer for completely free. And it's the first 3D imaging software to really do so. And so this is a representation of stars in the universe, and there's a lot of them, as you can see. Okay, and a cool feature in PartofView is fly mode, so you can kind of fly around the universe, look at different kinds of stars. But for our purposes, we really needed only stars that would be supernova. So after some experimentation, we came up with a command, which is thresh, which is a command thing, and SP type or spectral type index 1022, which are basically the supernova, the stars that we want. And when you run that, all of these stars will eventually become supernova. So if you look around, you can really identify stars or star clusters like Procyon. Sirius is for reference, and you see Denebola and all these stars that we don't really think about, like in our universe because they're not that famous. And you can actually even zoom in. Yeah, so it's just really a great tool to like explore our universe in general. And yeah, we had a lot of fun like looking around, experimenting with the code, and I actually got to talk to like someone who helped make the program, so that was a great experience. Yeah. What? Okay.
No.
Okay.
So basically what we came up with in our overall looking through all our data was that the general number of stars, the majority of stars, were low mass stars that would not result in supernovas.
We can also concluded that majority of the stars are close or near Earth, and so we're able to observe them.
And for future inquiries, we could do many things with this data set, which is really a great resource. And we could look at different parts of stars and how they function, and even different aspects of stars to understand more about them. Yeah, thank you for listening to our presentation.